meter bridge. Meter bridge works on the principle of Wheatstone bridge principle, in which the ratio of the two resistance P by Q and R by S should be same. Here we are using 1 meter long wire and try to divide this in terms of two resistors. So across point A and C, an external source is connected. In this left hand gap, we are connecting a resistance RB. In the right hand gap, we are connecting an unknown resistance S. Then this jockey is touched on the wire from A to C at some point where the balancing length is deduced. If at point B the balancing length is there, then this length is measured as L. The resistance of this wire is P. P is proportional to L. Since it's a meter long wire, the remaining length will be 100 minus L centimeter. This will be proportional to resistance Q. So P by Q ratio is equal to R by S. Then this point will be balancing point, since no current will be flowing through this arm where the galvanometer is connected. Galvanometer shows zero deflection. Then this is called this point B and D are the same potential, and this arm is the bridge arm. Then by taking the Wheatstone bridge principle as P by Q is equal to R by S, unknown resistance S can be calculated. So meter bridge is an instrument used to find the value of unknown resistance. AC is 1 meter long wire. It works on the principle of Wheatstone bridge. The ratio of resistances R and S, if it is equal to the ratio of resistances P and Q, P by Q is equal to R by S, current through the galvanometer will be 0. If point B is such a point, then it is called balancing point. Since resistance is proportional to the length, therefore resistance P will be proportional to L and Q will be proportional to 100 minus L. P by Q is equal to R by S, which indicates that L by 100 minus L is equal to R by S. Unknown resistance S can be calculated. S is equal to R into 100 minus L by L. Unknown resistance S can be calculated. At the balancing point, galvanometer G gives no deflection at all. At A and C, the galvanometer must have deflections in opposite direction, because then only zero deflection can be expected when the jockey attached to the galvanometer is moved from A to C. B is the balancing point. So noting this balancing point, length L and 100 minus L, P by Q is R by S, unknown resistance S can be calculated. Galvanometer. This is a device used to detect very small current. It gives the direction of electric current in an circuit. If I is the current flowing through galvanometer and theta is the deflection shown by it, then I is proportional to theta, or we can write I is equal to k theta. K is equal to I by theta. This K is called galvanometer constant. Theta by I, if we take it, that is called current sensitivity. Theta by I, that is 1 by K. So for a small amount of current, when the deflection theta is large, the galvanometer is said to be sensitive. Galvanometer can detect very small current. That means for very small current, the deflections will be large. And galvanometer is a very sensitive apparatus. And it gives also the direction of current in an electrical circuit. So theta by I will decide what is the current sensitivity. Ammeter. Ammeter is used for measuring current and in amperes. So it is an instrument for measuring current in an electrical circuit, and the current is measured in ampere. So let us see one by one all the points. It is an instrument used for measuring current in ampere. Basically, it is a moving coil galvanometer in which a low resistance wire called shunt is connected in parallel with the galvanometer. A galvanometer is converted to ammeter by connecting a very small resistance called shunt. By connecting a very small resistance called shunt in parallel to the galvanometer to save it from damage, because galvanometer is a very sensitive apparatus. The total current I is coming up. Current through the galvanometer is Ig. Leftover current I minus Ig goes through the shunt. So by using Kirchhoff loop rule here, we get it I minus Ig into S is equal to Ig into G. So the shunt required, we can calculate it as S is equal to IgG divided by I minus Ig, where Ig is the current through galvanometer, full scale deflection current through galvanometer. I is the total incoming current in the circuit. So suppose galvanometer allows 1 ampere current and the incoming current is 100 ampere current. So 1 ampere should flow through galvanometer for full scale and 99 ampere should flow through the shunt. The shunt should be clearly a very small resistance. So the shunt required to convert a galvanometer to ammeter will be S is equal to IgG by I minus Ig. This is the formula we require to remember and we'll be using in the numerical problem. The resistance of ammeter so formed. So now this has become an ammeter. Now this complete apparatus is called an ammeter with shunt. So earlier galvanometer, now connected with shunt, it looks like an ammeter. This is an ammeter. The resistance of ammeter so formed means resistance of galvanometer and shunt connected in parallel. So resistance of ammeter formed will be Ra, that is equal to Gs by G plus S. That means the resistance of galvanometer is, and resistance of shunt, if you see, resistance of shunt is very small to that of the galvanometer. So resistance of ammeter, since they are connected in parallel, will be still less than that of the galvanometer as well as that of the shunt. So ammeter is a low resistance device. An ideal ammeter is one whose resistance is equal to 0. Ammeter is a low resistance device. Hence it is connected in series in a circuit. It is always connected in series in a circuit. An ideal ammeter is one whose resistance is 0. So galvanometer connected with a shunt is called ammeter. The shunt required is IgG by I minus Ig. The resistance of ammeter is Gs by G plus S. It's very low and therefore ideal ammeter is one, his resistance will be 0, and therefore we can connect an ammeter always in series in an electrical circuit. Similarly, let us see about the voltmeter. It is an instrument which measures potential difference between 2 points in volts. A galvanometer can be converted to voltmeter by connecting a high resistance in series. So the resistance, this resistance is very high, then it increases the range of measurement. Since galvanometer has a full scale deflection for very small current and hence it can measure only small potential difference. However, if large resistance is connected in series with the coil, any desired potential difference can be measured. And it also reduces the error of measurement. If V is the desired voltage across these 2 points which we are going to measure, R is the additional resistance required, then if V is the desired range and R is the high resistance connected in series, then from the relation Ohm's law, V is equal to current through galvanometer Ig into total resistance G plus R. So we can calculate the resistance required. I is equal to V by Ig minus G. So this is the high resistance required to convert a galvanometer to required range of voltmeter. The total resistance of the voltmeter, now this is our voltmeter. This becomes our voltmeter. The resistance of voltmeter will be RV is equal to G plus R. This R is a very high resistance. So G plus R indicates the resistance of voltmeter will be very high, and hence it is always connected in parallel across a circuit whose voltage is to be determined or to be measured. An ideal voltmeter is one whose resistance tends to infinity. Voltmeter is a high resistance device. Hence, it is always connected in parallel across a circuit whose potential or voltage has to be determined. An ideal voltmeter is one whose resistance is infinity. For ideal voltmeter, resistance is infinite.